I guess the first thing to understand is that there's lots of different types of ventilation systems. There are whole house ventilation systems, there's single room ventilation systems, there are systems specifically designed to extract moisture from specific areas of our house. A range hood or a bathroom extractor fan, I would call a ventilation system, right up to balanced heat recovery ventilation systems in airtight homes. Positive pressure ventilation system is most commonly what people are talking about when they talk about a ventilation system. So I guess I'll describe that, and then we can describe any of the others as we need to as we go along. So positive pressure ventilation system is where you have a fan and a filter, hopefully a filter, a fan mounted in the ceiling space, normally of a trussed ceiling, and it'll take that roof space air and pump it directly into the house, normally through 3 or 4 or 5 ducted outlets. So what it looks like on your ceiling is a plastic circle about that big with a screw-in bit in the middle, so you can turn them down or make them flow more if you want to. And up in the ceiling space, you've got pretty much a box with a fan in it and a filter sock off one side of that, and 4 or 5 ducts coming off that, going to each of those outlets. And so that filtered air, hopefully filtered air, is just pumped into the house, providing positive pressure. And so when you pump a litre of air into a house, a litre of air has got to come out of the house. We don't want the walls of the house bulging. So as you pump a litre of air from the roof space, a litre of air from the living space gets pushed out through the cracks and gaps in the building. And the theory would be that air is moisture laden or pollutant laden or carbon dioxide laden, and so you're replacing that with theoretically cleaner air from the roof space, and then there's the potential for heating or drying with that air, or not, as the case may be. So it doesn't take much imagination to know that in a trussed roof with metal on it, which is very common in New Zealand, in the summertime, that roof space is going to be really hot. You might get up to 35 degrees up there easily. And so if you pump that air into your house is going to overheat very quickly. So we don't want to do that. But on a winter's day, you might, on that same tin roof, you might find air temperatures of sort of, 24, 25 degrees, something like that. And the theory would be that that's helpful to pump that air into your house. So balanced heat recovery ventilation is where you have, it looks similar to the homeowner on the inside, and that you have little plastic, ducts and your plastic little roses in your ceiling, but up in the ceiling space, it's completely different. And in fact, those systems really shouldn't be installed in a ceiling space. They should be installed inside the insulation envelope of the house. So kind of when we retrofit them, you're already onto a loser with those systems anyway. They should be designed into the house in the first place. But with a balanced heat recovery ventilation system, you've got basically 2 sets of ducts, and one set of ducting is taking the warm but polluted and wet and lacking oxygen air from inside the house and pumping it out. And another set of ducts that's bringing in probably colder but cleaner and possibly drier air from the outside. And it runs through a heat exchanger, basically. So you can take the heat energy out of the outgoing air and put that into the incoming air. So you can, and the theory is, and the truth is, you can change some of the air without losing all your heat energy that was wrapped up in that air, which is not what positive pressure does. Positive pressure pushes that warmed air out of the house. So positive pressure, you would kind of want a house that had gaps in it, which is most New Zealand houses. It's pretty impossible. You have to really specifically build from brand new if you want an airtight house. So positive pressure has the advantage, if you like, that most New Zealand houses are already leaky, so they're going to work a treat. They are going to push air out of the house. There's no problem there. Balanced heat recovery ventilation, which is as I say, a completely different kettle of fish, and there is more argument for those systems, but only if you have an airtight house that's been designed and built for that very purpose. And even then, you would need to be in the right climate zone to make them economically viable. And even then, there's still issues with the air change rates. For me, positive pressure ventilation systems are kind of sold one way, and actually in reality, I think work another way. So there's kind of sold on this positive pressurization thing, but the problem with that is, well, there's several problems with it. One is that if you're pushing out the moisture-laden air, you're also pushing out the heat-laden air, if indeed there is warm air in your house. So that's a bit of a problem to me. It doesn't sort of make sense. So they're sold on air change rates and positive pressurization. I suspect how they really work is air movement. So if we can keep the air moving, there's less likelihood of condensation forming. And, well, I'm kind of getting right into it now. The reality is these systems operate night and day. We're told by the kind of manufacturer, or it's implied that they will only operate when the ceiling temperature is higher than inside the house, but I know that to be not the case in most operating systems. They might flow on a reduced rate, but most of those systems actually will blow into the house at night. And the roof space air at night, there's no way it's warm. It's absolutely cold air that you're blowing into the house. So part of the suspicion is that how these things actually work to reduce the formation of condensation, and I'm going to come back to that point in a second, is partly what they're doing is dropping the inside temperature inside the house. So the dew point is formed by a combination of the inside temperature, the inside relative humidity, and the outside temperature. So the dew point is where condensation will form when all the characteristics inside the home environment are just right for that condensation to form. So, for example, we can look at if we had an indoor temperature of 20 degrees and indoor relative humidity of, say, 70%, and an outdoor temperature of, well, let's say 5 degrees, our dew point, which we can calculate off charts, so I'm just going to make one up. But our dew point that we can calculate off charts might be 13.9 degrees under those sort of circumstances, something roughly like that. So what that means is when that surface, whatever that surface is, and it's most likely to be a window because they transfer heat very well, so they get very cold. When that surface gets down to that 13.9 degrees or whatever it is off the charts, we can go, oh, well, that's when, with this much moisture in the air and these temperatures, that's when condensation will form. It's easy to have quite a high dew point in that your surfaces don't have to get that cold when it's really freezing outside. And the more moisture you have in the house, the higher that dew point's going to be. So when we've got a house that's really wet inside and it's a cold winter's night, there's condensation on the walls as well as the windows. And that's what, and in really, really bad houses, you wake up and the bed covering's damp because it's, that's become the dew point and the carpet's damp and the walls and everything's damp. And in the bathroom, we can get it on a reasonably warm day because we just massively saturate the air. We're at 98% relative humidity. So even when the wall surface is 20 degrees, you can still get condensation. That's the dew point. The dew point is a phenomenon of having a difference between an inside temperature and an outside temperature. So the less that difference is, the more flexibility we have with the dew point, I guess, is the truth of it. But we want to live in houses where it's really warm inside, even when it's cold outside. So we need to deal with and this is where the good building science comes in, we need to deal with the amount of moisture in the air. And these systems, positive pressure ventilation systems, there seems to be no proof that they change the moisture levels in the house at all. In fact, the evidence is and Beacon did a study on this themselves, the evidence is that during the day, the roof space air is most likely more damp, i.e. it has higher relative humidity, than the air inside the house. It'll be warmer than the air inside the house. So in the daytime, you're pumping in warm air, but it's wetter air. So warm, good, wetter, bad. At nighttime, you're pumping in cold air, so bad. It's arguably drier air because it's colder, so that's good. But the overall effect is questionable to me anyway, in that what these systems do really is they reduce the formation of condensation. Now, condensation is a symptom of a poorly performing house. It's a house that's getting too cold, it's poorly insulated, and has high moisture load in it. That's why we get condensation. So if we can look at the cause of the problem and fix that, rather than trying to kind of deal with a symptom of the problems, that to me makes a lot more sense. And really, they're not even dealing with the symptom, they're kind of masking the symptom, if you like. Because if the reality is that the way they're getting less condensation to form in houses that are running these systems is by lowering the internal temperature, that makes no sense to me. We know that cold houses in New Zealand are already an issue. We know that cold houses in New Zealand are killing people. So we certainly don't want to be adding to that in any way, shape or form. And that is my experience out in the field, is that people report, oh yes, we got rid of all the condensation. They're not monitoring their homes with hygrometers. So if they can't see condensation, they make the assumption that the house is drier. And arguably in some cases it will be drier because in some houses there wasn't enough ventilation initially. But I would argue in most houses with positive pressure, you're now massively over-ventilating the house to no good gain. So people report, oh, my condensation's gone, the house must be drier. And then you question them about the temperature and they go, well, it's quite cold. Yes, we do have to run the heat pump all the time, or the wood burner or whatever it is. So, but they're quite happy that they've got less condensation forming. But is the house drier? Often not. Is the house warmer? Often definitely not. It's definitely colder in the house. But because they can't see that end result of all these other problems, they're going, oh, great, mate, great. The analogy I give to my clients is I say, well, if you came to me for a bad back and I gave you an aspirin, have I fixed your back? No. The pain of your back's gone away, but I haven't fixed your back at all. It's going to be back tomorrow. So to me, selling a system that floods a house with air, I'm back to positive pressure now, that floods a house with air at high rates, sometimes damp air, sometimes cold air, seems to have, in most cases, the effect of lowering the temperature in the house, seems to have no effect on changing the relative humidity levels in the house overall. In fact, pushes them up in the day. But it's making people think that their house is performing better because they can't see the condensation. And that's actually my big issue with this, with positive pressure, is it's not, I don't care that some company's getting rich for selling something that doesn't really deal with the problem. That's not my business. My business is that there's an awful lot of people out there who think their home is performing better, therefore it's healthier, when in fact it's not, because of the temperature part of it. And is it any drier? No, not necessarily. So it's not that this is a benign thing. It's actually doing harm because you're taking people's focus away from what the real problems are, which is cold, damp housing. And that's fixed by ventilation, heating, controlling moisture, and good ventilation practices, not necessarily by positive pressure ventilation. And look, there's no question that condensation is a huge problem in New Zealand homes. There's no question of that. That's absolutely right. We need to address moisture levels in our homes. But I don't think this is the first port of call to do that at all. I think it would be the very last port of call to do that. There is no situation where I would recommend that you take your ceiling space air and pump it into your house at really high rates. No, I can't think of the situation where that is the solution. I really can't. I can think of situations where you'd want to insulate the property, heat the property, ventilate the property, control the moisture in the property, but I can't think of a situation where I think it's a great idea to pump tons of ceiling air into the house. No, can't think of where that would be. Really, home performance, which comes down to two things: temperature and relative humidity. That's what we're talking about in home performance. We want warm and dry. That's what we want. When we look at home performance, we need to look at four elements, or four performance parts, I guess, which come back to these two things: temperature and relative humidity. So on the temperature side, we need to look at how the building controls its heat loss, and then how we heat it, and that's going to determine the temperature range that the house is going to be in. And on the other side of things, we need to look at how we control moisture in that building or that house, and then how we change the air in that house, because we've got to ventilate. So if we look at those four components, have got to be in balance. It makes no sense to come into your house and say, well, you need R10 in the ceiling and R8 in the walls and R2 in the windows. You need triple glazing, and that makes no sense. You can't, there's no point in overemphasizing insulation or controlling heat loss. And there's no point in me coming into your home and saying you need 10 heat pumps or 3 wood burners. You wouldn't overheat a house. That wouldn't be good building performance practice or advice. And the same with moisture control and ventilation. Why would you over-ventilate a house? Yes, you need to ventilate a house. Yes, you need clean, fresh air in a house every single day if you can. Yeah, so the way to operate a home is to do those four key performance areas in balance. You know, it's kind of like a table. You don't want one leg longer than the others. You've kind of got to, you don't want to be heating a room up and then changing the air. So there's, you've got to think about these things a little bit, but it's not rocket science. So really, the ways to control moisture in a home are not to keep flushing that warm air out of the building, but it's to stop the moisture getting into the home in the first place. So there's internal sources of moisture and external sources of moisture. And it's kind of like, it's like an awful lot of things to do with building performance. If we actually get the basics right, we don't need to buy another bolt-on thing to try and fix the problem that we still haven't fixed in the first place. So external moisture sources, you need to get a ground vapor barrier under your house. If it's good enough for every rental property in this country, it's good enough for every property in this country. So get your GVBs installed under your houses. The amount of moisture that comes through that subfloor space and can get sucked into the house is enormous. Brands tells us 30 litres a day in that subfloor space area. That's a huge potential of moisture to be sucked into the house. Overhanging trees, foliage, all tight up against the house. I mean, I'm a plant lover, but we've got to allow the air circulation around our houses, and particularly that subfloor space, and we've got to allow the sunshine into the outside of our houses. If your house is sitting right next to a huge moisture source, of course it's going to be damp inside. Moisture is kind of like heat. It'll flow from the wetter to the drier part, just, through the air movement. So, I like to use exaggeration. So if your house was floating on pontoons in a lake, do you think it would be damp inside? Of course it would. But, and if it was sitting on a gravel bed with nothing around it, it would be much drier. Now, obviously, we don't want to live in either of those situations, but I use that power of exaggeration to say, look, clear the foliage around your house, make the outside as dry as you possibly can, maintain your gutters, make sure your downspouts are not putting great big puddles of water right underneath or next to your house. Inside your house, and this is really where a lot of the work needs to be done in this country. Anybody gets it, their house is cold, but the moisture thing is far more complex. We got kitchens, bathrooms, and laundry. And if we look at a kitchen, you know, cooking a meal might be half a litre of moisture, or it might be up to 3 litres of moisture per day. So that's, you know, as I say to people, how would you feel if I popped round of a cold winter's evening with a couple of, you know, 1.5 litre Coke bottles full of water and just sprayed them around the lounge? Would that be a good thing? And people go, no, you crazy fool, that would be a stupid thing. And I go, well, that's what you're doing when you're cooking without a range hood, that's effectively getting that moisture out. Showering, that's about half a litre per person per day. So if you've got 4 people in a home, that's another 2 litres. So there's Ian with his little spray bottles in the hallway and in the bedroom spraying another 2 litres of water around. And if we dry our laundry inside, you know, you take a full load of washing in the winter, you know, if you've got 4 or 5 in your whānau, that's a full load of washing probably every day. And you dry that on a rack in your lounge, that's up to 5 litres of water. So the problem is not keep changing the air in the house to get rid of the moisture in the air. It's don't put the moisture into the air in the first place. Get yourself a big range hood. If it's a rental, you have to have that now anyway. So if you're thinking it's only people that rent that make steam when they're cooking, you know, get one for yourself. A range hood is, I don't know, $500 and probably $300 or $400 to install on top of that, maybe another 500. So there's $1,000. That's cheaper than a positive pressure system. A bathroom extractor fan, well, they're probably a couple of $100 to buy and $300 or $400 to install. That's cheaper than. So now we're up to $1,700 maybe. And a vented dryer, I can buy a vented dryer for $500. So for half the cost of a positive pressure ventilation system, we can actually get rid of most of the moisture in the house at source before it even becomes a problem, rather than trying to deal with it all later once it's kind of affected the whole house or infected the whole house, if you like. So dealing with moisture at source is really the key. There's a couple of things we can't deal with, which is, you know, one is breathing. People insist on breathing all winter long. It's a bit of a problem in home performance. So there's nothing we can do about that. So we've got to focus on the things that we can do something about, which is, you know, our cooking, our washing, and our laundry facilities inside the home. And then you combine that with good ventilation practices, which, you know, which really is free and easy, and every house has that system already installed in it, which is windows and doors. All they need to do is be operated. And there seems to be this kind of idea out there that we're not responsible enough to operate our own homes, that it has to be on this automatic thing. You know, we can drive cars, we can raise children and feed ourselves. God forbid that we can't be taught to open windows and doors to ventilate our homes. I don't hold with this idea that it's too complicated in our modern lives. We still manage to cook our breakfast and clean our teeth and go to the bathroom. We've got plenty of time to open our windows and doors fully for 20 minutes a day. There's nothing more effective than opening windows and doors wide to change air in a building. That is proven pretty conclusively. You want to change the air in the room? Open up the French doors and the big windows wide and lots of part of the house. Positive pressure is sort of touted as the solution to any home, and that I can tell you categorically from the start that is not the case. So in New Zealand we have lots of what we call brick veneer buildings, and what a brick veneer building is really 2 boxes, an outside box and an inside box. And the outside box is the roof and the bricks and the ground, I guess, and the inside box is the wooden floor, the stud work and the plasterboard on the inside of the studs, and the ceiling. And so the air in a brick veneer building that is in the subfloor space, so that moisture-laden air that's coming out of the ground, is free to flow around the inside box through the stud space. That's how they're designed to operate, and up into that roof space and evaporate. That's fine and dandy. So if you put a positive pressure ventilation system into a brick veneer house, you're pumping the subfloor air, not the roof space air, directly into your house. And we know that subfloor space air is generally really, really, really damp. So they should never be installed in a brick veneer building for a start. A concrete tile roof. Now, concrete tile roofs generally don't have building paper underneath them. They're kind of worked on the assumption that the concrete tile can absorb a certain amount of moisture and then give off a certain amount of moisture, and it'll kind of self-regulate. So the air in a concrete tile roof is really damp as well. So they should never be installed in any house with a concrete tile roof. Skillion roofs, obviously, they can't really be installed in because this doesn't make any sense. But it's also the condition of that roof space. So if you've got decayed old pink bats or decayed old macerated paper or dead birds or dead rodents or anything disgusting in your roof space, you've got to think about the quality of the air that you're pumping into your house. My advice is if you're going into your roof space, you need to wear a respirator mask, not just freely have that air pumping into your living space. I've been doing this for a long time, going into people's homes, 12 years as an eco-design advisor. And, you'd roughly go to, I don't know, maybe 10 houses a week. The number of properties where people would complain about the cold and not the condensation, but the cold in their houses, and they had a positive pressure ventilation system, and then they would go, well, that's, we've obviously got this and it's wonderful and it's great. And I would explain how they work. And the common reply would be, well, it doesn't work at night because the roof space is colder. So I used to say to my clients, you do two things for me. Just before you go to bed tonight, carefully stand on a chair, be careful, and put your hand up there and see if it's actually blowing air. This is at night, 11 o'clock at night. And then the other thing is it warm air or is it cold air? So this has happened to me so many times that the next day I would get a sheepish phone call from the homeowner going, oh, yeah, no, yeah, yeah, no, yeah, it is blowing, yeah, and it's pretty cold air. And I'd go, well, there's your problem. So I mentioned very earlier that you're pumping supposedly and hopefully filtered air into your house. My personal experience is that not every positive pressure ventilation system has filters on it, number one. I had a sweet, dear little old lady client who said to me, oh, yes, they've just been and changed all my filters. And I said, I'm very sorry to inform you, darling, they haven't. You haven't even got filters. You're just pumping straight air. So that company had been charging her every year for replacing her filters. They never did the work. So that's a real shocker. So she's pumping God knows what contaminants into her house. And, yeah, you've got to be very aware of the overall condition of the house before you would put a ventilation system like that in. One of the specific examples I have, which is a horror story, was a rental property. They got me in to have a look at it because the internal walls as well as the external walls were running with moisture. I mean, literally running with moisture. I've never seen anything like it in my life. It had a positive pressure ventilation system installed in the house. They'd had the people round from that company to look at the system, and I can't remember all the details, but they said that there was nothing to do with their system and everything was fine. In fact, you should probably be running it more. It turned out that there was a water leak underneath that house. Eventually, through physical investigation, I discovered the water leak, and it had been running for quite a considerable time. So in that house, what they were doing was there was a massive moisture source under the house. The construction of the house allowed that moist air to get up into the roof space. So they were just pumping moisture at such levels into the house that, going back to that dew point, the relative humidity was so high that any surface became the dew point on a cold night. So an absolute tragedy.